Good morning, everybody. Buenos días a todos. Bill, be welcome to Costa Rica Club de Investigación Tecnológica. I will introduce you to the audience, but I want to, my heartfelt thanks for you to come and share your experience and knowledge with Costa Rican fellows. And I've read your work for quite a while, since the 80s. And in 2013, I conducted a seminar on software quality, and I read your paper on technical debt. So it's nice to have the author with us today.
Good.
So, muchísimas gracias a todos por estar aquí. Es un gran gusto presentarles al doctor Bill Curtis. Don Bill, le decía que yo lo vengo leyendo desde hace más de 30 años. Tiene 42 años de experiencia en software y trabajó muy activamente en el desarrollo del modelo de madurez de capacidades en software original del Software Engineering Institute en la Universidad de Carnegie Mellon, y también fue el autor principal del People CMM, que es el modelo de madurez de capacidades de personas, ¿sí? Ya en su segunda edición. En los últimos años, él ha estado trabajando en la industria de software. Es el científico jefe y vicepresidente senior de Cast Software, que es una empresa que se dedica a medir la calidad estructural del software. Estamos hablando de cientos de empresas y millones de líneas de código y demás, en que es parte de lo que le da información muy valiosa para la conferencia de hoy. Y además es el director ejecutivo del Consorcio para la Calidad de la Información y del Software, que desarrolla estándares internacionales para la medición del tamaño y la calidad del software. Le damos las gracias también a Richard Soley por habernos presentado con el doctor Bill Curtis. Es un honor para nosotros tener a Bill Curtis en el Club de Investigación Tecnológica. We are honored to have you today with us, Bill.
Thank you.
So without further ado, please.
Okay, I'm going to share my screen.
Yes.
Let's see, here we go. And buenos dias. That's actually all the Spanish that I know, which is embarrassing because my mother taught Spanish. But when she didn't want me to know what she was talking about, she would, of course, speak Spanish. So I'm going to give you some concepts and then some data on technical debt. In the course of this talk, I'll explain a little bit about what the Consortium for Information and Software Quality is. But the goal here is by the end of the hour, you will have a good understanding of technical debt and why it's important to manage it and, to the extent you can, to eliminate it. So first, the Consortium for Information and Software Quality was formed back in 2010 by the Software Engineering Institute at Carnegie Mellon University and the Object Management Group, which is an international standards organization. We were chartered to develop international standards for measuring the size and quality of software by measuring the source code, and then to promote these into international standards. So today we have a number of sponsors that fund the work that we do at CISC. We also have some partners, organizations that help us spread the word about software quality, help us get standards adopted throughout industry. So let's begin by thinking about what technical debt is. It really is the future cost of defects that remain in the code at a release. So therefore, it's a component of the cost of ownership, because if these are serious weaknesses, serious defects, you're going to have to remove them in the future. Often when you're building software, to get it done on time, you know you make decisions that are not optimal. but the code works. And you know that it's someday in the future, you're going to have to come back and refactor the code to remove the weakness. So that's a way technical debt gets created. From an executive point of view, anything that I have to spend money on to fix is technical debt because I have to pay for it in the future. So let's look at several ways that technical debt is created. It's structural qualities in the production code that's out running in the business. And the first component, whoops, as I kill the screen, the first component is the principle of technical debt, which is the actual cost of fixing the problem. The effort it takes for you to correct the problem and then test it and put it back into production. Now, until you fix the problem, you may be paying interest on the debt. And the interest would come in the form of the extra effort you have to spend working with code that's too complex or code that is has poor performance characteristics, so it costs you extra cycles on the machine. And if you're in the cloud, you're paying for those cycles. So interest is all the costs you accrue because of those problems until you fix them. So that's what technical debt is. There's principal and there's interest. But when you expand the financial metaphor, you'll find that there's also business risk, and these have costs. There is the liability you would experience if you had an outage during major retail hours and lost a good deal of business. There's also liability you would have if there's a security breach of your system and all your customers' credit card numbers were stolen and sold on the dark web. So there are liabilities to technical debt, especially those that relate to reliability or security or performance. In addition, there is opportunity cost, because the time I spend fixing a problem, the time I spend fixing technical debt is time that I don't have to build new code, time I don't have to build new features and capabilities that would help the business expand their revenue opportunities. So the nice thing about the technical debt metaphor is that it allows us to talk about software quality in terms that the business understands. We're putting quality into financial terms, and the business understands costs. They understand it when we talk about the liabilities, when we talk about the lost opportunity cost, when we talk about paying back the principal by having to spend time fixing problems that we didn't fix before we released the code. So that's the concept of technical debt expressed in financial terms that the business can understand. Now, there are a number of ways that we use the technical debt metaphor in business. First, it helps us calculate the cost of ownership, because I want to calculate the cost of the effort to remove the technical debt. And that's an estimate. I have to estimate the cost of how much effort will it take me? What does that translate into dollars or euros or pesos or any other currency? Then the business is going to want to know, what is the risk of your IT system to the business? The business auditors want that information, and we rarely have numbers to give them. So the nice thing about technical debt is that it quantifies some of the risk that the system presents to the business, the risk of it going out during retail hours, the risk of a hacker breaching it and stealing credit card numbers. In addition, it's a very good way to explain software quality to the business. They don't understand software, and they don't want to, and they shouldn't have to, but they do want to understand why it costs so much. So this gives us a way to explain why we are spending additional money on fixing problems during development, so that we don't have this technical debt creating risk for the business and additional cost to IT once it goes into production. And then finally, it gives us a way to look at the quality of all the applications in our portfolio. So in doing that, it gives us a way to prioritize how we assign our resources to different applications to try to manage the quality across the whole portfolio. So those are some of the uses of the concept of technical debt. You can also write this concept into contracts you have with your outsourcers and system integrators and providers by saying that there are forms of technical debt that we do not want to see in delivered systems, and you have to remove it at your cost. There are certain kinds of security violations that should never be in the code. There's reliability problems that we expect you to fix before we put the code into operation. So some of the concepts behind technical debt are useful when you're dealing with your vendors and your providers. So how do we estimate technical debt? Well, there are several sources of data that we can use. There are test results and static analysis, and this tells us about the problems in the code, especially the structural problems that we should go fix. Then we want historical data on maintenance. What are our costs? How do those costs get created? And then there is typically the records in finance about how much effort we spent. So how much effort did we spend on this application, especially how much effort did we spend to fix problems? So when I put those three sources of data together, I put the problems, I put their historical costs and the amount of effort that's going to drive those costs. When I put those three together, then I can begin to estimate the principal of the technical debt. In essence, I'm able to estimate how much will it cost me to fix all these problems in the future. And I'm only talking about severe problems. You're not going to fix a problem that doesn't have any impact on your operations and is something you would defer forever. So we really are only talking about fixing problems that really present risk to the business or excessive cost to IT. So some of the data I'm going to present was collected using a system developed by CAST Software. That's the company I work for when I'm not directing CISC. CAST has a static analysis technology, but it works at the system level, so it can swallow entire applications, analyze them, and give a system level view of the problems that are in the code, both at the code level and at the architectural level. So we can analyze now somewhere in the neighborhood of 50 languages and 50 frameworks and different systems. And those go into the analysis engine where we can evaluate over 1,200 rules of good coding practice. Not all of those are critical. Only about maybe a quarter to a third of those rules are actually critical and need to be removed. And then we break that into 5 different kinds of weaknesses. The first is we break it into, let me show you the kinds. We break it into 5 different types of weaknesses: performance, robustness, which is reliability, security, transferability, which you can translate to understandability or comprehensibility. It's how easy is it to understand and read the code. And then finally, changeability. How easy is it to change the code? So you can see that the last 2, transferability and maintainability, basically translate into how maintainable is the code. Whereas the first 3, reliability, security, and performance, translate into the risk the code presents to the business. And so in each case, I've given you some examples of maybe 4 types of weaknesses that would fit into those categories. So for security, you can see the well-known SQL injection, cross-site scripting, buffer overflows, uncontrolled format strings, and what have you. Those are severe security weaknesses that you need to get removed from the code so that hackers can't exploit them to break into your system. So this is how we analyze the code. This is how we represent the weaknesses that we find in these 5 categories. And I'm going to use these in a few slides in presenting the data.
Bill?
So first, yes.
Sorry to interrupt. I was just wondering, I mean, CAST is just one of these tools. I imagine there's other tools that people can use.
There's Sonar does some of this. Synopsys has a tool called Coverity. They do this, especially for embedded code. Synopsys is especially good at embedded code. CAST is good at IT type systems. Sonar Cube does a good look at looking at the lower levels, the code level of the code. So there's different tools out there. This is the one we use because it gave us ability to look at the architectural level as well. So there's 3 levels that you need to think about software quality. The first level is at the code unit itself. This is what I do as a developer. I write a component, I do my unit tests, I submit it to the build, and at that point, I believe it's the most perfect piece of software ever written on planet Earth because I built it. However, that piece of code now that component has to work with lots of other components, probably built in the same language or a framework that works with that language, that are spread across what we'll call the technology level. Usually the business logic is in a similar technology. And now my components have to interact with many other components in a much larger, more complex system. But the biggest problem is that that's not the whole application. An application is a stack of technologies. I've got the user interface level. It may be interacting with a mobile device or some other device. There's my business logic. There's the database, there's macros and frameworks that might be working with. And then at the bottom, there's the database and whatever language you're using to interact and query the database. All of these are probably written in different languages. So I typically, in a large application, you'll have 5 or 6 different languages that the code is written in. And this is where the worst problems arise. They're at the system level, the architectural level, and they're represented by all these interactions. So just knowing that you have a good component, you've written a good piece of code, doesn't mean that that piece of code won't have problems when it begins interacting with other pieces of code at other levels in the system that are written in different language. That's where the big problems are. In fact, let me give you an example of that. This is I'm going to talk about architecturally complex defects, and those are the ones that exist at the system level, where it's interactions between different components, probably written in different languages that sit at different places in the system. So there was a study done of a telecommunications system in Canada, and it was done by one of the major system integrators for the customer, the big telecom customer. And what they found was that 92% of all the weaknesses were at the code level, at the component level. They were within a single module or within a method or within a class or what have you. They were small. Only 8% were at the architectural level. And this is typical. When we've analyzed most systems, we found that somewhere between 5 and maybe as much as 15% of the weaknesses are at the architectural level. It's very small, typically 10% or less. The problem is the cost of repairing them. That 92% of code weaknesses only accounted for 48% of the overall fixing effort. The big problem with architectural weaknesses is the cost of fixing them. They found that 50% of all the effort they spend fixing defects was spent fixing those 8%. Why is it so difficult? Why do they have to spend so much time? They found out it was because they spend 20 times as many fixes, as many bills, trying to find all of the implications that defect has for other parts of the system. So it interacts with other components, and it takes a long time to get that cleaned up to where all the components are now working in sync and they're not contradicting each other and creating problems in operation. So it took almost 20 times as many fixes to correct an architectural level problem as it did a module level problem. So we're going to call these architecturally complex defects, and we see some components in the system that seem to be a central point through which a lot of these weaknesses pass, that they're involved in a lot of these architecturally complex defects. And these represent architectural hotspots. You know, they're code components that cause a lot of problems because they're interacting through a lot of architecturally complex defects. And we find that the major impact you can have on making a system better, on improving the quality of the system, is by eliminating these hotspots. And typically we find that you can't go in and just keep fixing it and fixing it and fixing it. Typically what you have to do is rewrite it. In fact, rewriting it will take less time than trying to correct all the different interactions it has with all these different architecturally complex defects. We typically find that these components were written by someone who either didn't understand how it interacts with the system or wasn't a very good coder. And so the best thing to do is to throw it out, rewrite it in a way that it works with all the different components that it is connected to, that it's coupled with. So in fact, we find that if you can find these highly coupled components, often there's no need for them to be that coupled to the system, and it's better just to refactor them and simplify their complexity. So the data I'm going to show you comes from a repository that's associated with the CAS tool I just showed you. This is an earlier study we did where we had 745 applications. They came from 160 different companies, businesses, a few government agencies in various countries. And there were 14 countries that these 160 organizations existed in. They were in North America, Europe, and India. And there were 321 million plus lines of code. And within those 321 million lines of code, there were 60 million, almost 60 million violations of good architectural and coding practice. So you do the division, that's pretty bad. That's a weakness almost every 5 to 6 lines of code. So there's a lot of problems in the code out there in the world. This shows the size of the systems that we were working with. You'll notice that some of these were large. There were 7 systems that were over 5 million lines of code. We had 86 systems that were over 1 million lines of code. The average was around 300,000 to 400,000 lines of code. So you can see these are significantly large applications. And here's the kinds of businesses that these applications came from. You can see primarily they were from financial, insurance, and IT consulting, you know, the big system integrators. A lot also came from telecom and manufacturing. And then there were a number of other different kinds of industries and some from government agencies. So this is a good slice of a good representative sample of the kinds of applications that are out in the world. So this is the article that we built based on analyzing those 745 applications. It was published in IEEE Software, which is a major technical journal, several years ago. And in that, we developed a table. Now, I know you can't read the numbers on the table very easily unless you get real close to your screen. But the bottom line is we looked at different ways of calculating technical debt, and we looked at a number of different ways of analyzing it. And on average, the most conservative way of looking at technical debt, the most conservative way of calculating technical debt is that it would cost $3.61 per line of code to fix it. And we're not talking about all the weaknesses. We're really talking about the serious critical weaknesses that you need to fix in the code in order to reduce the risk or reduce the cost. So, there's our conclusion. Even when measured with conservative formula, the amount of technical debt in most business applications is formidable. The estimates of technical debts can be a powerful tool to aid management in understanding and controlling IT costs and risks. So this is why we think it's valuable to calculate technical debt. It really gives you a sense of what the risk is to the business, the cost is to IT, and why we have to spend money to make code better, to reduce the risk and to reduce the cost.
Bill?
Yes.
Sorry to interrupt again.
Yeah.
Would it be a reasonable assumption to think that if the hourly cost of developers in Costa Rica is less than in Europe and the States, then our technical debt should be a bit lower per line of code?
Yes, it should be. And even much less in India, which is why a lot of the maintenance work is done in India, because the costs are so low. Although, having said that, the cost of labor in India is rising rapidly. I think that within 20 or 30 years, we'll see a global level, close to a global level of cost for an IT person, for a developer. Because I see in India, people leave and go to other countries, go to other companies every year or two to get a higher salary. So we know that that's going to have a big impact on the cost of software development, software maintenance in the future. Okay, this shows how technical debt is distributed.
Sorry, Bill?
Yes.
Marcelo has a question.
Okay, Marcella, yes.
Hi, Bill. Just one simple question. Have you tried to compute the amount of technical debt using something like functional measures, something like function points or cosmic points or something like that, and not directly in dollars?
We could do the cost per function point. We didn't have a function point, automated function point counter available when we did these calculations. We do now, because we've developed that into an international standard. It's an ISO standard now, but unfortunately we didn't have that when we did this study. My guess is, since function points are typically much larger than lines of code, that number would go up per function point. But there's a real problem with function points, a serious problem when you're looking at technical debt, and that's function points do not measure the non-functional components of the code. And most of these architectural weaknesses are in the non-functional components. And in most business applications, the non-functional code is over 50% of the code in the system. So we need a measure that captures both the functional and the non-functional, and then allows us to compute this as a total of, let's say, we'll call it implementation points. But we've got to count for the non-functional code, because that's where many of these serious critical weaknesses exist. Almost all of the security and reliability weaknesses are in the non-functional code. So here's how, in fact, it breaks out. This is the percentage we found of these critical weaknesses in different types of violations of good practice. So you'll see that 40% was in this transferability. It was roughly how understandable is the code. 30% was in how changeable is the code. And then you've got the other 30% in robustness, performance, and security, which is the business risk. Now, just because only roughly a third of the weaknesses are in the area of business risk, it doesn't reduce the risk to the business. Some of those are very serious problems that have to get fixed, or the business is at significant risk. Whether it's a performance issue that slows down the way the system works, or it's a security issue that allows a hacker to break in. But typically 70% or so of what we find in technical debt is in the area of maintainability. And we looked at this across languages. You can see there's a number of languages there, and the percentages stayed reasonably consistent across the various languages, from COBOL to Java to .NET to C and other languages. So we found this was a fairly consistent breakout across different languages that are in different applications.
Sorry to interrupt, Bill.
Yeah.
Is this a percentage of dollar value of technical debt?
No, this is percentage. This is when I look at the total number of critical defects, this is the percentage of those critical defects that fell into each of these quality categories.
Good, thank you.
Yes, sorry, I should have explained that better when I started, but yeah. So now I want to look at how this affects productivity. Let's look at the next release and look at the productivity of the work I did when I go to the next release. Right there, I want to measure. When I want to measure productivity from release to release, I want to look at the volume of new code that was developed, the volume of existing code that was modified, or any code I deleted from the previous release. So I get a total accounting for the work I did in making these changes to the code, additions, deletions, and other kinds of work. And I want to divide that by the total effort that I expended in that release. And that gives me a sense of what my productivity is, the amount of work compared to the amount of effort. That's a traditional definition of productivity, certainly the one that's typically used in software. So let's see how people think about productivity. Typically, they think about it as having a productivity baseline, right? And I'm going to argue that there's no such thing as a productivity baseline. A baseline tells me that this is my standard productivity. It'll be the same from release to release to release because I have the same people, we're using the same tools, working on the same application. So our productivity level ought to stay the same unless we make major improvements. Now, I'm going to argue that's not true, that is a myth. It just doesn't work that way, that in fact, productivity is a monotonically decreasing function when you compare the amount of work to the amount of effort. Why? Because every time I release a new version of the code, I've probably increased the technical debt, right? There's incremental increases to technical debt with each release because I couldn't fix all the problems that I created. We can fix some of them, but not all of them. That just makes the code more complex and a little bit harder to work with, and therefore my productivity goes down. And it just continues and continues and continues until I finally decide to do something about it and fix the problem, right? So until I take action, we're going to see a continuing decrease in productivity over time because it's harder and harder to work with the code. So let's visualize that. Let's say we're in release N, that could be release 30, let's say, and I've got my development work, I've got rework. You know, that's the rework is the effort I spend fixing defects that I just put in the code when I developed it or when I modified it. So that's work I did right now within this release to fix those problems. But then there's problems I didn't fix, and those are the unfixed defects from release N. And those are sent forward into release N+1. So now I've got, I've got work that I have new development work in this next release. I've got rework to fix the problems in this new work, but I've also got this rework to fix problems from the old release that now are bad enough they have to get fixed. Plus, I've probably created some new defects, right? I've got the unfixed defects from the last release and these new defects I created in this release that I haven't fixed, and those all go to the new release, right, to release N+2. And so now I'm just building up and building up technical debt over time. And until I do something about it, I'm going to constantly decrease my productivity. It will be harder and harder to work with the code. So that's how technical debt builds up. what do we call release N+2? Well, eventually we call it legacy code. It's a messy, just a swamp that no developer wants to go into without protection. And it's just a mess until you get it fixed up. And it decreases performance and it increases risk to the business. So how do we reduce technical debt? Well, this is just a possible process you could use to fix your technical debt. And it starts with executives setting a policy that we must spend time reducing technical debt. If executives don't set that policy, the developers will never have time to do it, because you'll get all these priorities from business, from IT. Your entire sprint will be filled up with new stories, new work, no time to fix old defects. So you need a policy that says either every third or fourth sprint will be dedicated to removing technical debt, or each sprint we'll spend 10 to 15% of our time fixing technical debt. But without a policy, it'll never get done. And then once they have that policy in place, we can begin, the application managers can begin setting reduction targets and building plans for what they, how they want to reduce that. Let's say I want to reduce half my technical debt within the next 2 years. How are we going to do that? And then we want to go and analyze the code, right? And see kind of what kinds of technical debt we have, and then build plans for dealing with it, build plans for action, and what we're going to do in each of the next several sprints, what types of technical debt we're going to reduce. Typically, I have a backlog that identifies weaknesses that need to get fixed, and so we want to have a plan for doing that. And then we go in and remediate those violations, and then we want to test those results and make sure that what we're releasing is now better code than it was before. And then typically we want to report our results to the business. We want them to know how we're continuing to make the IT systems that serve the business, how we're continuing to make them better, more reliable, more dependable, and trying to reduce the cost of IT. So this is just a potential way to go about reducing technical debt over time. You won't do it all in one release. It will take a number of releases over a year or more to get the most serious parts of the technical debt removed from the system, if you have a system that has a lot of technical debt. So how do we translate this into business measures? Because a business doesn't care about reliability and changeability. What they care about is actual business things that create business value or reduce business risk. So we look at our 5 quality characteristics and we'll say, what kind of operational problems do they create? And you can see, robustness, that results in outages, slow recovery from outages, performance is degraded response, down at the bottom, changeability, excessive effort to continue working with the system. So IT just keeps costing more and more, and you're getting less and less. And so when we look at the business side of this, we start seeing, what does reliability mean? It means availability. How often is your system going to be down, and how often is it available to you and your customers? Performance, if it's an internal looking system, then it's how efficient is my workforce that uses this system. If it's an external looking system, how satisfying is this system for my customers to work with, because they get quick responses. Clearly, security is protection of confidential data, whether it's your own proprietary data or data your customers have entered into the system. Transferability, well, that's just the productivity of your people working with the system. The more understandable it is, the less complex it is, the more they can work much more quickly and understand the code. We find that in maintenance, 50% of all the effort spent in maintaining a system is spent on trying to understand what the code is doing. So any way we can cut that cost dramatically reduces the cost of maintenance. And finally, changeability is how fast can I get new functionality into operation for the business. How fast can we give them new competitive capabilities? They understand that quite a bit. That's really more than anything else. That's what they want from IT, is getting things into operation fast so I can be competitive or satisfy my customers. So this is an example from a very, very large telecommunications company. And they had a lot of systems that were not performing well, that had lots of defects. It was costing them a fortune. They weren't having time to build new capabilities because they were having to spend so much time fixing serious defects. So they finally, you can see the red dotted line going down the middle. That's when they started using a static analysis technology to identify the worst parts of their technical debt. And this is the results they saw. You can see that the gray parts of the bars there is the time they spent fixing code defects, the time they went in to fix software problems, and the blue is having to fix non-code problems, things that were not in the code but system level things they had to fix. And so you can see that once they started analyzing the code and finding where the technical debt was, finding where the most severe violations were, they could dramatically reduce the effort over time they spent fixing defects, release by release, because as the code got better, they had fewer defects to fix, and they injected fewer defects in the code they were building. It was easier to write, make a modification to code that's in good shape, that's not complex, and therefore you don't make so many mistakes. So they just found overall they not only reduced their cost, they improved the performance of this application to the business itself. This was across releases. This is data from a large system integrator in Europe. It's 21 systems or 20 systems for their clients that they were maintaining for clients. And as they began correcting technical debt, you'll see on the bottom there's a maintainability index. It's really a total technical debt index where they were looking at technical debt. And you can see that on the y-axis, what we're showing is the logarithm of the number of tickets that were placed against each of those systems. And what you can see is that as the maintainability index improves, 4 is the top number, 1 is the bottom number on this. But as the maintainability, it improves and the technical debt is reduced, the number of tickets is dramatically reduced, because this is a logarithm, remember. So they were very satisfied. In fact, what they found is that it cut if they could make a change of 0.24 on this scale in their maintainability, it cut their maintenance activity by 50%. Dramatically fewer tickets, dramatically less effort to fix them. So this really proved to that system integrator and their customers that spending time reducing the number of defects, eliminating a lot of the technical debt, had enormous impacts on the cost of maintaining the system. And finally, this is a large bank, very large bank, and as they improve the software quality, that's a technical debt index, that software quality on the x-axis, and they looked at the number of incidents in operation and what those incidents cost in terms of lost revenue and effort to fix. You can see that they went from their worst applications that the total loss was about $2.5 million in terms of operational problems and business costs, all the way down to their very best applications. The loss was only about $3,000 because there wasn't a lot to fix, and it wasn't causing problems in operation during normal business hours. So they were convinced that time spent reducing technical debt, fixing these problems, had a huge impact on the costs in IT and the cost of the business as well. So finally, I want to just give you a couple of slides telling you a little bit about what CISC does. As I said earlier, we're an international software measurement standards organization. We build standards that we submit to OMG. And if they're approved, they become OMG standards. OMG is a large international standards organization. They have standards for things like UML and CORBA and a number of other IT related capabilities. And so we were chartered to be a special interest group in OMG focused on software measurement. And we've looked at size and quality measurement. We've produced 9 standards. One of the standards is combines 4 of the other standards. So you look at the top, the size standards, you can see that our automated function point standard, and this is a standard for automating the counting of function points, that is now an ISO standard. It's been accepted by ISO 19515. So that's an international standard for automating the counting of function points. And it's focused on helping static analysis vendors like Synopsys and Sonar and Cast and others develop systems that can count function points in an automated way. And that reduces the enormous variability you get with manual counting, and it dramatically reduces the cost over time. And in the quality area, we originally produced standards for reliability, security, performance, efficiency, and maintainability. Those are those are half the quality characteristics in the ISO quality standard 25010, which lists 8 quality characteristics for software. We've automated half of those. We updated them to combine both IT and embedded code, combined them all into one document, automated source code quality measures. That is in the ISO system. It has a number. You can see it on the website of the ISO website. We expect that they will publish it in April. You can't access it from ISO until they formally publish it, which we're told will be April. But that standard is really built for the vendors of static analysis technology to know what weaknesses, only critical weaknesses, the ones you have to remove, are in this standard for calculating those 4 quality characteristics. But for those of you who want to hold your vendors accountable, you can say, we expect that you will achieve certain levels of quality as specified in ISO IEC 5055, because that specifies, or you can pick 1 or 2 of the quality characteristics. Here's what you have to achieve in security. Here's what you have to achieve in reliability. So that's how CISC works. Our most important work becomes an OMG standard, and by far the most important components of those standards are moved over to ISO through the OMG fast track. So finally, this is the CISC website. I invite you to come become a member of CISC. Membership is free. Anyone can join. Because CISC is paid for by its sponsors. The sponsor organizations put up the funds to support our work in the website and other things we do. In the website, we have all the standards. They're free. So the standard you'd buy from ISO is free on the CISC website as an OMG standard. We hold annual conferences on cyber resilience, with security, reliability, and a number of other things. And we have people from the government and industry come and talk on some of the critical issues in cyber resilient software, cyber secure software. All of those talks, all of the PowerPoint decks from those talks are available in the website. So there's a lot of information there. There's language you can use in contracts to specify the quality you want for these various quality characteristics. So I encourage you to join. These are the companies that we have members from. Now we've got members from all the Fortune 100, most of the Fortune 1000, and so membership is free. Just go to the CISC website. There's a button you can push and answer a few questions. We send you a password and you're in. So with that, let me open the floor for questions.
Thanks a lot for that, Bill. That was very good.
Thank you. Excellent.
One obvious question, Bill, is if you don't have a software analysis tool, you're basically dead in the water.
It's going to be very difficult to analyze the structural or architectural quality of a large system. You just can't do it manually. When systems were small, we could do it in code reviews or formal inspections, but these systems are now in the millions of lines. My latest quality report, we had 1.3 billion lines of code from 2,500 applications. I mean, those, and you know, we had like 75 that were over 1 million lines of code. So these systems are now way too large, and you have to have automated tools. That's the whole, really the whole purpose of DevOps pipelines, is to automate as much of the work, of the routine work as we can, so that developers can spend their time, you know, designing code and designing test cases, and then let the system do the routine work, so that you can spend your time doing the things that are complex and take some creativity. In fact, CISC is now working on measures for DevOps environments, because all of a sudden lean becomes a very important concept when you look at a pipeline. When you look at, I mean, we're creating something that looks more and more like a manufacturing pipeline in DevOps. You know, code is not a product. Code is not the kind of product you manufacture in the same way you manufacture a car or a radio. But the concepts, the lean concepts, can be translated into a way that they work with IT environments, with development environments. And so that's what we're trying to do, is come up with measures for this new way of building code in a much more efficient and speedy way. Yes, yes.
Has CAST or other companies made some sort of taxonomies for architectural defects, like the ones you mentioned?
Yeah, only in the sense that they're related to the quality characteristics I described: reliability, security, performance. So they would classify an architectural defect into one of those categories.
Okay.
And that's the way ISO does it. I've made sure that CISC is consistent with ISO 25010, which is the standard ISO software quality standard, describing the quality characteristics. I'm actually a co-author of that standard now, and I've got them to add security, and we're looking at changing one of the characteristics to be flexibility, with scalability as a sub characteristic, because that's more consistent with the effort to modernize software. You know, break things into microservices and whatnot. So I make sure we're consistent with ISO. ISO 25023 is the ISO standard that defines software quality measures, but it only describes them at the operational level. It has very few that are at the code level, at the system level. So they describe reliability as availability or recovery time. They don't describe it as poor error handling, you know, or things that will break the code. So CISC supplements ISO 25023 by identifying the weaknesses related to these quality characteristics that you can detect at the code level. So we describe quality at the code level, whereas 25023 describes it at the operational level. So they supplement each other. In addition, every code weakness, every CISC weakness, every weakness we use in calculating these measures now has a CWE number. CWE is the Common Weakness Enumeration, and it's a repository originally of all the weaknesses that we knew hackers could exploit to break into systems. So originally there was over 800 security weaknesses in the Common Weakness Enumeration. But with CISC being formed, they expand that to any kind of weakness that's a risk to the system. So all of the weaknesses in CISC are now a part of the Common Weakness Enumeration. It's maintained by the MITRE Corporation with funding from the U.S. Department of Homeland Security. And the Common Weakness Enumeration Repository is an ITU standard, International Telecommunications Union standard. So that means it's recognized by the United Nations. So CISC, everything CISC does, to the extent we can, we follow standards. We make ourselves consistent with ISO or UN standards.
Thank you.
Other questions?
There is one in the chat.
Oh, okay.
From Professor Alexandra Martinez. Should I read it, or do you want
yes,
to
let's see. Well, yeah, you better read it. It's probably in Spanish.
How is technical debt affected by trends like agile methodologies, for example?
Yeah, actually, that's a great
microservices.
Yeah, it's a wonderful question, and I'll break it into two parts. One of the consultants at Gartner, one of the major IT advisory services, found that agile methods were actually rapidly increasing the amount of technical debt in systems. And it's a problem when you have a short cycle time. You've got a sprint and it's 2 weeks or 3 weeks. You don't have a lot of time to be fixing the problems that you created and fixing, code. Complex code that you created in a component that you realize I could simplify that, but you don't have the time because you've got to deliver the code to the build and get it out in the sprint. And so they find that technical debt seems to be increasing as a function of agile methods, and in some cases it's increasing fairly rapidly. Now, and as sprints go forward, they keep getting filled up with requests from the business and from IT, and they don't have time to go back and fix the technical debt they've created in many cases. So that's a problem. There's no policy that protects time for eliminating technical debt in the future. So in some cases, agile methods are building technical debt at a legacy pace. And that's a real problem. So there has to be some protection within a sprint for the percentage of time you're allowed to go back and fix technical debt from previous releases, refactor the code or fix an architectural problem. Now let's see, there was a second part to that question.
Yes. What was about releasing services or microservices architectures that have code in different languages, for example?
Yes, well, that accelerates the problem, doesn't it? I mean, microservices are both a blessing and a challenge. They're a blessing because it simplifies things. I don't have to coordinate with the entire rest of the organization to make change to code. I mean, in theory, my team has responsibility for the following components, and we're self-managed and self-empowered, and so we can make the changes, fire it down the DevOps pipeline, and it goes into operation and everything's fine. In practice, over time, as people begin to degrade a microservices architecture by making connections to each other's data repository without going through proper APIs or other data management capabilities, you degrade the architecture, and it's no longer really a microservice-based architecture. It's starting to look more and more like legacy. So you have to protect the architectural integrity of the way you're going about maintaining a microservice-based system. Second, the additional complexity you get, once you break it into microservices, there's lots of moving pieces. One of the problems people find is that if they've got 3 or 4 different microservices doing the same thing because they were built by different people who didn't realize that another microservice exists that did essentially the same function. So they become large and complex, and you have to manage the integrity of the functionality, so you don't have too many pieces doing very similar functions. That's an interesting new form of technical debt, right? And then just the overall complexity of having lots and lots of microservices, and it's hard for anyone to understand all of them and how they all interact. I mean, in theory, if you honor the APIs, then you'll keep reasonably safe. But there is a lot out there in a microservice, and the complexity of that environment can be challenging. So the more you can do to simplify the complexity, to make it easier to understand what microservices are out there and what a new microservice may want to interact with in terms of using other features, the better. So it is challenging. The technical debt within a single code component is still there because that's within a microservice, and that microservice can have a lot of technical debt built up inside it that needs to be refactored. But you also have to really make sure you maintain the integrity of the architectural structure of the microservice compendium, or else you'll lose the value of having microservices, and you'll have created a tremendous amount of architectural debt. Other questions?
¿Más preguntas? ¿Podemos traducir? Yep, I have one small question.
Okay, sure.
You mentioned the developers level who are the finest programmer in the face of the world.
We all think we are.
Yes. And is that the level that SonarQube is able to attack? No higher levels, or?
Well, they're moving more and more to get system level, try to do system level analysis. So they're getting there. They're getting there.
Okay.
Originally they were heavily focused on code components, and now they're expanding out. So CAST and Sonar typically have been there for quite a while.
Yes.
And there's others. I haven't mentioned all of them. There's lots of different competitors out there. There's a brand new one called VeriPrism that actually has a very fast, efficient system because it uses newer technology. So they're one of the possible, and they do architectural level analysis.
And I am a professor, so this question is more linked to my previous one.
Sure.
And probably to Professor Alexander Martinez one is, what can we do to learn from what you are researching and seeing in the field, so that new generations of software developers learn better practice to avoid building technical debt?
Yeah. Well, there is, if you're a professor, I assume your university has access to IEEE and ACM publications through the standard system. And there is a conference that I think is sponsored by either IEEE or ACM. The Software Engineering Institute's heavily involved in it, on technical debt. Okay. It's typically held every year at the International Conference on Software Engineering. It's one of the sub-conferences. Okay. And there the leading researchers get together and present papers and argue a lot. And there was recently, they got 40 of us together in Dagstuhl, Germany. There's a series of conferences that the German government sponsors called the Dagstuhl conferences on various topics in IT. And they publish books with all the different papers. And so we had one 3 or 4 years ago on technical debt, and it brought a lot of the researchers together. So I think if you look, you can probably go into the IEEE and ACM systems and hunt through IEEE software, transactions on software engineering, and some of the other, and especially look at the conference papers where you see a technical debt conference. And I think you can keep up pretty well with what's going on in the world, in the academic research world.
Thank you very much. There's a question from a colleague from Banco Nacional, Jaime Murillo. He asks, how much time would it require to perform a diagnosis of technical debt at a bank in Costa Rica, which would be a mid-level bank in the US?
Yeah, so it depends really on how big the system is. Okay. Because if you're going to look at the technologies that look at the architectural level take longer because they have to process more and compare more, parts of the system. And typically, something that's several 100,000 lines of code would take a few hours, typically. You can get in minutes, piece of freeware off the net will analyze your component. but to look at all the interactions. And the more interactions you have, the more coupled the system is, obviously, the longer it takes to truly analyze at the architectural level. So, but most of these within in less than a day, it's usually a few hours to get the analysis done.
Yeah, but I mean, but this bank, I would think, I mean, and there's several people from that bank here, you can correct me, but I would say they have millions of lines of code in dozens of languages.
Yeah, well, some of these systems do handle multiple languages. Doing that increases the time a bit because I've got to parse all the languages and then rebuild that abstract syntax tree and all those connections. So I can do an architectural level analysis. So I know CAS does it. I'm pretty sure Synopsys does it. There's probably several others that can do cross-language comparisons. The thing to do is to just go out on the internet to the various websites and see what they claim. The National Institute of Standards and Technology at the U.S. does at least every year, or I think maybe it's every 2 years, they have an analysis called SAMATE, where they invite people to submit their static analysis technologies, and it's really focused very heavily on security level weaknesses, but it does analyze how effectively these languages can detect, or how effectively these tools can detect a range of weaknesses in a body of code. So that's another place to look for comparisons. But I think the thing to do is to look at the websites and then ask them to give a list of the kinds of weaknesses that they detect. And most of them will have that list, and then you can decide what you think the best solution is for your technology. I know Veriprism, CAST, pretty sure Synopsys, and several others can do multi-language analysis.
There is another question from Nelson Cotto from the Central Bank in Costa Rica. He asks whether there is any way of knowing and controlling or differentiating technological obsolescence. Sorry.
How much COBOL do you have? The amazing thing when we analyze these systems in banking and to some extent insurance, but especially in banking, the amount of COBOL is staggering. It's massive. In fact, most of the critical systems are still in COBOL because they work. They're very, very complex. There's no documentation, and the guy that wrote it is dead. Right? So people are scared to go back and redo all the COBOL because they don't know everything that's going on, and they know they'll make a mess of it. So they build the Java code around it, sort of as a wrapper around the core COBOL system. So, and COBOL is sometimes challenging because the average size of a component in most modern languages is roughly 50 lines of code. In Java, it's roughly 30 lines of code. In COBOL, it's 600 lines of code. So it's just a different world, and banks are loaded with COBOL. Now, if you don't have a lot of COBOL, you have a blessing. The gods have smiled on you. But I think look at the companies that I've mentioned that do multiple language analysis. It does take a little longer, because you got to build the abstract syntax trees, integrate them so you can get a good vision of the overall structure of the application and identify the weaknesses within that abstract representation. But I think, go ahead. I think there was another part to that question.
And to know whether it's a good idea to migrate the thing into a
well, I think migration is a strategy. Right. And some people migrate part of the system into microservices, but not all of it. There's reasons to go to microservices. One, you want to move things to the cloud so your operational costs will be less. You want to simplify the system so that it's easier to make changes rapidly and get new functionality into operation. You want to be able to separate to some extent the work of teams, so that teams can work independently with their own set of components, make changes to those components, shoot them down the DevOps pipeline, and get them into more rapidly into operation. And that, you know, that's one of the advantages of a really well architected microservice system. So I think you have to decide what parts of an old legacy system you want to turn into microservices. You probably want a strategy, because some of a legacy system is so complex and not documented, and it's going to take a long time to know that you have broken it into microservices in a way that is faithful to the original functionality of the system. Some things you can pull out very rapidly, right? So you have a strategy that says pull out things rapidly that you can pull out, and then carefully decompose this massive chunk of highly coupled legacy code that's, you know, more complex than most people can collect in their head. But there's no requirement. You know, I mean, there are a lot of people who have moved some of their systems into microservices, but not others, because they felt the cost was too great and the risk was too high, or the benefit wasn't sufficient to justify the effort to do it. So again, it's a strategy that looks at cost and your IT strategy going forward.
There's other companies coming from other questions from the YouTube.
Okay.
And also from people who are attending here. This is one from Professor Gabriela Marin. Do different actors within institutions or organizations have different perspectives or different aspects of technical debt? Like
yes,
different
absolutely.
Industries or things?
Yeah. There are two fundamental approaches to technical debt. The original, developed by Ward Cunningham and published at the conference in 1992. I think it was at the Object-Oriented Conference in 1992. Was that you know, I make suboptimal design decisions to get code out quickly, but I know I have to go back and fix it later. That's technical debt. It's conscious. I know I've done it. I did it on purpose to get the code out quickly, but I do know in the future it has to be fixed, right? So common weaknesses like a SQL injection or a buffer overflow, they wouldn't consider that technical debt. That wasn't a design decision I made to get the code out quickly, a suboptimal decision. However, the CIO and the CEO, they don't care. If I've got to spend money to fix it, it's technical debt. It's a good way for me to think about things that I have to spend money on to fix. I don't care whether it was a conscious suboptimal design decision or whether it was just a stupid mistake. It doesn't matter to me. I have to spend money. So the industrial approach, and it's the one I've taken, is that anything that has to be fixed, that's critical enough to be fixed, is technical debt, because that gives me a much better estimate of the cost of corrective maintenance. You know, what's my cost going forward to fix all this stuff that's just got to be fixed? And so I think it's more, the definition I use is more useful for industry. But academically, there's interest in the cost of making suboptimal design decisions because I just had to get code delivered. And that would help me think about the trade-off between some additional schedule or resources versus, you know, getting things done quickly and creating these suboptimal chunks of code.
Excellent.
Okay.
Thank you very much. There are more questions coming.
Hay más preguntas.
What are your suggestions for approaching executives?
¿Cuáles son sugerencias a la hora de abordar a los ejecutivos?
Delia, I can hear you.
Oh, okay.
Yeah, I can hear you.
I'm sorry, hold on.
That's okay.
I got disconnected for a while and now I don't know why I'm in English. Hold on a minute. I don't seem to be able to.
I'm in English because I'm too dumb to learn any other languages. I flunked German. I flunked German. I flunked French. You know, it's amazing. I even have a degree.
Hold on. No me
I
estoy
passed
pudiendo
Latin because you don't
pasar.
have to speak it.
No me puedo pasar y no sé cómo.
Bueno,
Okay.
¿Dónde está
Well, let me go ahead and answer the question, and we can.
the suggestions for
deal with that later.
communicating the realities of technical debt to executives in companies.
Yes. I think if you can express it, you know, I showed you that chart that expressed it in terms of different forms of cost. There's the principle of the cost of fixing, there's the interest. This is money we're paying, you know, effort we're having to spend until we get it fixed, or it's cost we have because we're using too many cycles for inefficient code or whatever. There's also liability. What if the system crashes? What do you lose in terms of customer interactions? If somebody breaks in and steals all the credit card data, what is that going to cost us? So the more we can put the cost of critical violations into these terms, the easier it is to talk to an exec. I mean, they understand the business risk. They understand hackers breaking in and you know, costing them millions. I mean, I'm now argue sometimes that we're in the era of 9-digit defects. And people say, do you mean 9 digits? You mean bits or bytes? And I say, well, I mean dollars and euros. I mean, we're literally seeing problems that cost over $100 million or 100 million euros to fix. You know, Target had a breach of all their credit card data. They figured it was about $200 million in liability. The Equifax breach, that, you know, almost put them out of business. They're figuring that could be $600 million. RBS, the Royal Bank of Scotland, had a crash, basically, and a bad update. And when it was backed out, the fellow that did it destroyed all the customer data. And so, you know, 22 million Britons couldn't get to their bank accounts for 3 weeks, couldn't pay their mortgages, couldn't buy food. I mean, it was a disaster. They figured that was about 175 million British pounds, which would be somewhere closer to 250 to 300 million dollars. So, this, you know, the worst of these is costing a fortune. For a mid-sized bank, it won't be that bad, but it's still, you know, would have an enormous impact on the quarterly profit. So I think if we express the most critical weaknesses in terms of the potential liabilities, in terms of the potential costs going forward for, you know, the more we have to spend in IT because the code is badly structured and it just takes longer to work with, and we're creating more mistakes when we do it. The more we can put it in those kinds of financial terms, the more executives understand what it really means to them, because they really care about the numbers.
Thank you very much. I have 4 more questions.
By the way, before we go, don't use the term software quality. Executives hate the term software quality. They don't care. You know, if you talk about outages, they care. Security breaches, they care. Quality, they don't care.
There's a question here about who should be in charge of software quality. What are best practices around that?
Yeah, typically it would be good to have, you know, sometimes we call it a software quality officer or software quality director. Could be the person that's in charge of software process improvement. If you have such a person, it could be, if you have an audit organization focused on IT, it could be them. But it's someone who has the time to go from application to application, evaluate their practices, look at the data on the amount of technical debt in their system, you know, the number of critical violations, and knows enough about software development and maintenance to make sensible recommendations about how they can improve the overall quality of the system and reduce the technical debt, and the practices they need to put in place going forward to make sure they don't have a recurrence of building bad code. So I think it needs to be someone who combines those functions. It could be an audit person, a quality assurance person assigned to IT, could be a software quality officer that has the time to go around to look at how different applications are being built and their quality. You know, But it needs to be someone who has the time and the responsibility and the assignment for doing that kind of work, making recommendations, evaluating where they are, looking at how they're performing their process.
There's another question regarding requirements. Is there any way to address technical debt from requirement solicitation, analysis, and validation? Is that
there's a whole separate body of I don't know if there's a large body of work, but a whole separate thought process on requirements debt. And if you have a lot of it, it enters, you'll build that into the system, and then you've got a system with conflicting features or features you didn't really need, or other kinds of problems. And so I don't know of a lot of automated tools. That's not an area I've followed that would detect those kinds of things. The best defense against a lot of requirements debt is to, number one, make sure you've got a number of people giving you requirements who are looking at different aspects of the business issue that you're trying to implement, that you're trying to automate. Don't just get don't get input from one person alone. Problem with agile methods, they typically only deal with one person from the business as part of the requirement for what you put in a Scrum. But I mean, for those of you in banks, how does a bank grow? It grows by acquiring other banks. And all those other banks have their own process, and they don't want to change. They want to keep doing it the way they've always done it. So when I build a set of requirements for a new banking system, all these different people with all their different processes want their process in the requirements. And now I've got a mess. I've got 16 different ways to do the same thing. And that's a requirements mess, which gets translated into an IT mess. So this is a problem that has to be solved up at the requirements level. First, you need to simplify the process, right? You really need to, the more you standardize the process across all your divisions, all these different banks you've required, the easier it is for IT to build a sensible system that's not too complex and whose architecture you can maintain over time, and in which you'll build less technical debt. But the more that requirements run wild, the more the system gets needlessly complex. And that is in a form, that's the result of requirements debt, of having too many different ways to do the same thing. I'll give you an example. We went into a bank one time, and they asked us to look at their credit card processing process. And we analyzed it over a period of a couple of months and working with them, and found out they had 183 different processes in their credit card operation, and they had 16 different ways to open an account. It was a nightmare, right? And so after that, in that 2 months of working with them, we simplified it down to about 50 basic processes and only 3 ways to open an account. And we think we could, if we worked with them more than 2 months, we could have made it even simpler. But, that process should be done, that rationalization of the business process, standardization of the business process needs to be done first. And then when you develop the requirements, they're better organized, they're simpler, there's not as many of them, and there's less requirements debt that moves forward into code. Into creating technical debt in the system that it's and now every time one of these different units in the bank changes, I've got to go in the code and find out where their particular process is and change it. And it just gets complex and time consuming. So the business owns some of the challenge in some aspects of technical debt. Next question.
Maybe this is the last one I have here.
Okay.
So far. This is from a colleague who works in software engineering, particularly regarding maintenance and evolution. And I will translate. It's his perception that the software industry has produced software for solving diverse problems, but not much time or resources for following up the process of development and maintenance, so that it addresses technical debt. He's talking about the process of developing or maintaining software and having some software support for that so that it's
reducing.
reducing.
You're talking about removing technical debt that we're spending all our time developing
or
and maintaining.
it.
Yeah, and well, and that's a challenge. I mean, you look at agile methods. You have a short cycle, and you don't have a lot of time to go back and fix things. You know, you get your unit tests done, and then you submit it to the build. And if there's tests that come out in integration or system tests, then they go into the backlog. You know, maybe you have time to fix them, but they may end up in the backlog, and they never come out of the backlog because you keep getting loaded up with new requests. So the problem is we don't spend the time up front in trying to reduce the amount of technical debt before we submit to the build or before we declare it's finished code and potentially ready for delivery, ready for production. And that has to be a policy. I mean, really, nothing's going to change if there's not policies that change it. So again, saying we may spend, 10% of our time fixing previous technical debt, 10% of our time going back and fixing some of the technical debt that we created within this release. That has to be a matter of policy, and the executives have to enforce it. And if they don't, then, the developer doesn't have the authority to do it. They're going to get yelled at if they take that time. And so the only time they'll have to do it's on nights and weekends, and that just wears them out, and they make more defects because they're tired. So this really has to be a matter of policy. And so the executives are responsible for creating an environment in which you can measure and manage technical debt. And therefore, what you're doing is reducing the risk to the system, reducing the risk to the business, and reducing the cost to the business. And that's why technical debt is a useful term, because it helps the business understand that. Okay.
Well, thank you very much, Bill.
Thank you.
Yeah, I'm going to ask everybody to please open their mics and their cameras so we can thank Bill properly, por favor. Abran todos el micrófono y las cámaras para despedirnos y para agradecerle a Bill como se lo merece. Yo creo que I think we're all very pleased. It was a great lecture, a great presentation, and very useful. I already got comments over the chat of real business applicability that they're going to take.
Well, good luck. And I really enjoyed having a chance to talk with you, and good luck on going back to your banks and other businesses and having some real impact.
Everybody's going to get rid of the technical debt by next week.
Yeah, okay.
Thanks a lot. Muchas gracias.
Thanks very much.
Thanks.
Gracias.
Muchas gracias.
Thank you. Gracias.
Bye-bye.
Excelente.
Gracias. Muchas gracias. Chao.
Muchas gracias. Gracias a todos por venir.
Muchas gracias. Hasta luego.
Gracias por la invitación. Muchas gracias.
Por el evento. Excelente.
Hasta
luego.
Que la pasen bien. Chao.
Even the dog enjoyed it. Good.
Oh. We have two here.
Yeah.
Thank you very much, Bill. It was great to have you here.
Great.
And,
thank you. I enjoyed it. Goodbye.
I followed some of your newer writings.
Oh, good. Well, I'm working now on a number of things with CISC and very quietly building a meta model for building maturity models. And I'm working with the healthcare world right now to build a maturity model for helping them adopt better practices. So, there's a lot of exciting work to do.
Good.
Okay. Thank you.
Thank
Goodbye.
you very much, Bill. Have a nice day. Bye-bye. Hasta luego a todos. Steven, yo ahorita le contesto. Chao.